Yes, I decided to take a break from restoring the Sony and to take care of something which I bought a few months ago and of which I'm really happy I bought it. I think some of you might already know what this is. And if I show you a close-up of the logo on the box, why yes, it is a tube tester. And more specifically, it's a Sencore TC162. I bought it on the internet and I can't say it was cheap. I can't even say it's a bargain. Although, let's say, as prices go nowadays for these kind of tools, the price was, say, well, the market price. So not too low, not too high, somewhere where those machines, the prices range where those machines are sold. And yeah, well, I got the machine itself, so the tube tester. I also got the setup chart that goes with it, and as you can see, it contains a lot of tubes, and I can test almost any tube from, say, the early 30s, I guess, although, let me see, no, I can't test the 4-pin tubes, apparently, but let's say I will probably be able to test tubes from the late 40s till the early 70s. It's even possible, if I read the booklet correctly, to test compactrons with it. And as some of you will know, a compactron is in fact a vacuum tube which contains several vacuum tubes. So it was a trend they started right before the transistor started to break through, where they, to save some space inside a TV or a radio, well, mainly TVs, they grouped several tubes into one vacuum tube, and they called it compactron. Those things, I guess, had something like 12 pins or maybe even 14 pins. And that's what this socket here is used for. It has many pins. So I didn't count them, but if rough estimate would be 14 pins. Anyway, I bought it, and I bought it, as the saying goes, as is. So no guarantee that it would work, no extras. The only thing I got, you could say, as an extra was the setup booklet. Something which, well, is rarely sold together with the equipment to which it belongs, because there are quite a lot of sharks out there who want to make a buck, an extra buck, by splitting the machinery from its original booklet. Yeah, so that they can make an extra buck. But I was lucky, and I could buy this one with its booklet, which seems to be complete. As far as I can tell, it has seen rather heavy use, but it looks complete to me. Okay, in any case, the fact that I bought it as is means that chances are the insides of the tube tester have never been looked at since the day it left the factory. So I thought it would be a good idea to at least have a look inside to see whether everything is okay. Although I'll admit I already used it and it seems to work properly, but still, I think it wouldn't be a bad idea to open it up and see whether it looks okay inside. Also, I unscrewed the 4 screws from the top cover, and indeed it looks like I was right, and that is sufficient to open it up. So, well, let's have a look together at what's inside. I didn't really have a look inside, I just lifted it up a little bit. So let's go and see what's inside. Oh, it's pretty heavy. Okay, well, this is nice. Okay, this makes it a bit easier to work on it. So, okay, hang on, I just have one hand here to work with. So let me take the box and move it out of the way. So, as you can tell, it's just a steel box. Very dirty, so I'll have to clean it. But aside from that, it looks okay. Just a few dead bugs, and that's about it. Okay, so we'll clean that afterwards. Okay, so now, this is the inside of the Sencore. Yeah, and as you can tell, it's neatly wired, yeah, with a whole row of switches to insulate the pins of the tubes. But we'll go over the working of the tube tester a bit later. So anyway, what interests me first of all is to see whether there are no burns inside, and it seems to me there are no burns inside, which is good. They also went the cheap way for doing some stress relief on the wire by putting a knot in it. Well, I'm not particularly fond of this knot thing, so I might just release the cable and then undo the knot and place something else, you know, but we'll see. Anyway, except for a bit of crud and some dust, the whole thing looks okay. Now, the transformer has a lot of output wires, as you can tell. So it has only one primary coil. I peeked at the schematic, of course, so that's why I can tell you. This has only one primary coil for 110 volts, which is kind of unfortunate, and I'm seriously considering of maybe finding a sort of a way to make it work on 220. We'll see about that. Anyway, so it has a transformer with a primary only for 110. And then it has a lot of output wires. And I mean, when I say a lot, I really mean a lot. Let me see. I would hazard to say 10 output wires. Yeah? And each of these wires provide a higher AC voltage. Okay? So it starts at about 1 volt AC. And it goes all the way up to, wait, let me see. Oh, I would say something like 50 volts. Yeah? Something like that. Something like 50 volts filament. So from 1 volt to 50 volts. Which I would hazard was used for example, compactrons, which I think ran on 18 volts or even 30 volts. So yeah, that's quite interesting. But okay, what interests me most of all is this little board here, mounted right on top of the meter. Okay, so I'm rather pleased to see that it contains, except for one electrolytic, which you see here, it contains ceramic capacitors and plastic capacitors. And these ceramic and plastic or propylene capacitors, they are good forever, you could say. These rarely go bad. And there is, since this is a so-called transistorized meter, there is one transistor right here. Now, strictly speaking, this is not a transistor, but a FET, okay? A field effect transistor, or a FET, which is mounted right here. And there's only one of it, of those inside the whole thing, okay? There are a couple of diodes hidden somewhere, but really, I think the main point of concern is this capacitor right here, this electrolytic, which is a 50 microfarad, if I'm not mistaken. Yep, 50 volts. You can see it on the side there. Okay, so I am going to replace this capacitor. Just out of safety precaution, I am going to replace this one. And I'm thinking about building in a fuse holder. Now, I am a bit reluctant to drill a hole inside the casing. So probably I'm not going to drill a hole. But what I am going to do is I am going to mount a fuse holder. And to be more precise, I'm going to build in the fuse holder where the 220 comes in. So right about here. Okay, so I'm going to mount that. I soldered together a 47 microfarad 50 volts with a 3.3 microfarad 50 volts, as you can read for yourselves. Now, hang on, I'm going to go close up. Okay, there you go. So I measured this one, and it produces, or it has a value of about 50.2 microfarad, which I would say is pretty close to the value required. Okay, so what I'm going to do now is I'm going to release this board from the back of the meter, and or at least I'm going to try to. And as far as I can tell, that's done by unscrewing these two nuts here at the back, these two big nuts, so that I can lift this PCB a little bit to unsolder this capacitor. Now, if that proves a bit too hard to do, I will simply snip loose this capacitor and use its leads to solder the new capacitor in. But we'll see. Okay, interesting detail, where normally on capacitors the ground or the cathode is indicated with arrows, black arrows. In this case, the plus is indicated with arrows. So that's a detail to keep in mind, okay? These arrows do not indicate the minus of the capacitor, but the plus, the anode, okay? Replacing the capacitor was, well, I would say really painless. I gently lifted the PCB off the multimeter, the dial of the meter by releasing the two top nuts, and as you can see, it just lifted right off, and I could unsolder the capacitor. So this pin here, right here, and that pin over there, this pin here. So by unsoldering this pin and that pin, I could simply remove the old capacitor and place the new one inside. Now there's an interesting little detail you have to take into account when releasing that meter, which is that you need to put a sort of locking nut over the pins like this, okay, on each pin one. So yeah, like this. There you go. And only then, when you place those two locking nuts, you can slide the PCB back into place like this. Okay, and what you do next is, once you've installed the PCB back like this, you place again a set of locking nuts which look like this over the screws. I need a small wait a minute, a small tool to place them because my fingers are a bit too fat. So I'm using this plier, a needle nose plier, to put back the locking nut or ring over the screws like this. Okay, and once the locking washers are in place, I place the nut back like this. Okay, then we screw it gently back. No need to put a humongous amount of pressure on those nuts. Just as long as they are tightly screwed, but not enormously tightly, it is okay. You know, because they don't provide for mechanical strength. Well, not really. The only thing they do is provide for a good electrical contact. So that's what I'm going to do next. Okay, I fitted in a fuse holder, as you can tell here, and I put in a 175 milliamp fuse, which is more than enough for this device. So I mounted this fuse holder, okay, in a non-permanent way, in the sense that at a later stage anybody who would own this tester could still unmount this without any visible damage to the case. Still, personally I feel a lot safer having this fuse mounted to the tester. Okay, so I mounted a fuse holder with fuse. I also mounted a new electrolytic, the only electrolytic in the whole tester, and I also replaced a screw which was used to hold down the transformer to the casing, or to, I should say, to the cabinet front. And as you see here, the original screw looked something like this, and this is the new screw. Okay, I used a long screw with a wing nut, okay, so that I can apply enough force to hold down the wiring to the chassis, but not apply too much force. So as long as my finger can hold down the wing nut, I'm not applying too much force. As soon as the wings start to force my fingers away, I know I'm applying too much force. Okay, so that's done. So, well, the rest of the chassis looks pretty neat, looks really clean, yeah. And okay, I'm going to measure the power resistors you see there, just to see how good they still are. They should be 150 ohms. So let me see, one here, one there. Okay, and the value is 161 ohms. Yeah, but that's still within the 10%. It can vary, because if you take a close look at the resistor, you'll see there is a tolerance marked of 10%. So the value can drift to 165 ohms, and that would be still okay. So let's measure the other one now. So between, let me see, this pin and that pin. Okay, and that one measures 155 ohms. So this one is actually closer to the value which is inscribed on it, which is 150 ohms, as you can read here. And this one is 161 ohms. Okay, so these two power resistors are still within tolerance. My guess is pretty much all the other resistors will have drifted off somewhat of their original value, being carbon type. Say for example this 10,000 here. Let's measure it just out of curiosity. Come on, come on. Okay, here we go. Okay, so it's a 10 kilo ohm and the multimeter says 10.2 kilo ohms. So that's still well within 10% value. And I'm really glad for that. So, like I said, all the resistors will have drifted off a bit of their original value, but they will still probably be within 10%. So this is great. Chances are I won't even have to recalibrate the tester. Now, if you look at the front, that's also interesting. You remember that the front, wait, hang on, is this panel here. Okay, so I unmounted it, and I unmounted it by undoing nuts which hold down each of the switches. Yeah, and there was one chicken head knob like this, and the other knobs were more square like this, or I would say coffin-like, coffin-shaped. Now I doubt that this switch was a chicken head knob. It must have been originally the same type of knob like this one. But it probably broke off, and along the way somebody replaced it with a chicken head knob. Okay, fine, no problem. It does what it needs to do, and I intend to keep this tester as equipment and not as a let's say some kind of collection device. Okay, this is really a working instrument. Okay, anyway, so if you unscrew the bolts that hold down the switches, you can simply lift this cover off. And what you see then are the pin insulation switches. So these are each of the switches. And so suppose you would put down pin 3 and say pin 6 and then pin 7, and you would you disconnect pin 3, 6 and 7. Now suppose you want to start all over again. There is a reset switch, which is here, you know, which on the cover is marked like reset pin elimination. Okay, so the mechanism is really quite simple. You push this button to the right, and this metal plate is attached to 2 pins, so 1, 2, and you can see there is a groove etched or routed into it, and the groove runs diagonally. So what happens is when you push to the right, the metal plate goes up, and what happens is it pushes up all the switches. So if you take a look at these 2 switches, see, it resets the switches in the on position. So, and it can do it with all the switches at one go. In one go, up, there you are, all resetted. Okay, so that's a nice little trick. Also, the plate is held down by a single steel coil or steel spring, and the spring still looks okay. So the very last thing I'm going to do now is to clean off all the parts and the front and everything. And once that is done, I'll remount everything into the case, into the cabinet, and then we'll have a go at trying it out on a few tubes. I nearly forgot to show you. So this is the original electrolytic I unmounted from the Sencore, the TC162 Sencore. And as I told you before, the arrows do not indicate ground like you would usually see, but they indicate the plus. Okay, so be careful if you ever think about replacing this electrolytic in your own tester. Okay, so don't confuse these arrows for ground. These do indicate plus. Besides, you see that the ground pin is actually attached to the casing of the capacitor on one side and is held up by insulation material on the other. So you should sort of a little bell should ring in your head telling you that you should be careful. Okay, so now anyway, why did I replace it? Well, I'll show you why. If you give me a second. So let's see the multimeter here. Hang on. Okay, so let me see. Yeah, this is the right orientation. Okay, hang on. Okay, hang on, because since I broke my little tripod, I really have to use an alternative method to get around the problem, and that doesn't make things easy for me. Okay, here we go. Okay, hang on. Okay, there we go. So it says 64.4 microfarad. Okay, so that's horrible. That's more than 10% off. So yeah, well, electrolytics, whenever you see them, you should replace them. No compassion. Okay, I'm mounting back the chassis into the cabinet. Now, one more detail I forgot to mention is all the isolation switches, as you can see, are slide switches. Okay, so, and normally they have a red knob like this. Well, the red knob is attached really like this. It's really nothing more than press fitted to the knob. So you simply push it on like that, and that's it. We're going to try my refurbishing of the TC162 Sencore tube tester, and we're going to try out a number of EL95 amplifier pentodes. So mini tubes like this one, okay, and the equivalent, the American equivalent, is a 6DL5. Okay, so we're going to measure a few, let's say 2 or maybe 3, and let's see now. You should set the insulation pin or the pin elimination switch to, let's give you a close-up, to pin 7. Okay, so it is indeed pin 7. Okay, so you lower it to eliminate a pin. Okay, right. So then the second switch, the filament switch, should be set to 6. So 6 volts, which it is over there. Okay, and then the knob C is the load on the grid, should be set to C, which it is. And then finally the switch D should be set to 1. Okay, so that's what it is. Okay, so now we're going to test, first of all, whether the tube has any shorts. Okay, here we go. Okay, all the switches are set to their correct position, so the A row, B, C, and D. So the very first thing we need to check on the tube is shorts. But before we can, we need to heat up the tube, so, or rather make the filament heat up. So we switch it on by putting the switch to shorts. Okay, let's see. And indeed, as you can tell for yourselves, the filament is indeed glowing. Okay, so I mean just a few seconds of waiting time is sufficient, you know, just to get the filament up to glowing sufficiently hard, and it is. Okay, so the very first thing you need to do is check a tube for shorts, and you do that by setting the function switch to shorts and then turn the D knob all the way through all the numbers, and if you can all the way back, just to see whether this light, which is the shorts indicator, lights up or not. They say in the booklet that there's only effectively a short when this switch lights up permanently. So if you see it flash even for a very short while, that basically doesn't mean there is a short. Okay, so anyway, here we go. Watch the little light here. Okay, seems there are no shorts in this tube. Okay, so what we do now is measure the emissions. So to measure the emissions, we set the switch to emission. Now I should say that when you switch on the meter, so it stands on shorts, you should zero the meter with this knob here. Okay, so, and it's exactly 0 for the moment. Okay, so it's okay. Now let's put it to emissions, and this for shorts. Load it up. Okay, so here we go. Emissions 0. Well, you should read the upper dial. Okay, emissions 0. Okay, so let's try out grid leakage. Oh dear. 100% grid leakage. Okay, so this tube is basically, you could say, shorted. Right, that's not good.